Many complex systems, from large organizations to software platforms, eventually seem to reach a state of unmanageable complication. The natural impulse is to search for a specific error, a single point of failure. But this state is often not the result of a mistake. Instead, it's the outcome of a natural evolutionary process. In this explainer, we will deconstruct that process. We'll begin by looking at a common assumption about failure, then define what a system is and the pressures it operates under. From there, we'll examine how small, rational repairs can create a cycle of growing complexity. This leads to a state of gridlock, where meaningful change becomes nearly impossible. And finally, we will see how this outcome can be understood not as a failure, but as a natural state for certain types of systems. The entire process really starts with a fundamental paradox in how we perceive failure. There's a significant gap between the common assumption of how systems break and the reality of how failure actually emerges. We tend to assume that big problems come from big identifiable mistakes, a single bad decision, a faulty part, or one person's error. But the reality in complex systems is quite different. Catastrophic failure rarely has a single root cause. Instead, it emerges from the unforeseen interaction of many small, seemingly minor events and decisions, each one perfectly logical on its own. So, to understand how these interactions build up over time, we first need to define the basic components of the system itself. At its core, any system, whether it's a company, an economy, or a piece of software, is simply a network. It's a collection of parts that interact with each other according to a set of roles, all working towards some kind of overarching goal. We can break this definition down into 4 key components. First, you have the agents. These are the people, the teams, or even the automated modules that perform actions. Then you have the rules, which are the procedures that govern behavior. Third, the connections, which represent the pathways for communication and influence. And finally, the purpose, which is the system's overall goal. Now, these components don't just exist in a vacuum. They are constantly being shaped by 2 fundamental and often competing pressures. The pressure to perform pushes the system to meet its current goals as efficiently as possible. At the very same time, the pressure to adapt pushes it to respond to new challenges, threats, and opportunities from its environment. A system that's constantly being shaped by these pressures is what's known as a complex adaptive system, or CAS. In a system like this, nothing is static. The agents and the system are always co-evolving. Every interaction between agents actually modifies the system itself, little by little. So how exactly does this constant evolution lead to unmanageable complexity? Well, the engine driving this process is a simple repeating pattern, the cycle of local fixes. This feedback loop is sometimes called a fix that fails. It starts when a symptom of a problem appears. In response to that pressure to perform, an agent applies a quick, local solution that solves the immediate issue. But that fix, no matter how well-intentioned, creates unintended side effects somewhere else in the system. Over time, these side effects surface as a brand new problem, which then prompts another local fix, and the cycle begins all over again. There's a related pattern that can accelerate this whole thing, called the second system effect. After a first, simpler system is successful, there's this really strong temptation to load the next version with every single deferred idea and improvement all at once. This sudden burst of additions can dramatically increase the system's complexity in a single jump. The key thing to realize is that each time a local fix is applied, it adds a new rule, a new procedure, or a new dependency to the system. And while each of these decisions is rational in isolation, their cumulative effect is what really matters. Let's look at how this complexity actually accumulates over time. We're shifting focus now from the individual cycle of fixes to the long-term consequences of that cycle repeating over and over again. So imagine a system in its early days. The connections between agents and rules are few, they're clear, and they're pretty easy to understand. You can trace cause and effect without much trouble at all. But then, a problem arises, and a fix is put in place. This fix adds a new connection or dependency. It could be a new reporting requirement or maybe a small process adjustment. The system has now become just a little bit more complex. As more and more fixes are added to solve the side effects of previous fixes, the web of interconnections just gets denser and more tangled. What was once a simple, clear diagram now starts to look like an incomprehensible knot, and the system's behavior becomes much, much harder to follow. This tangled state is known as tight coupling. It means the components of the system are so interdependent that a small change in one part can ripple through the entire network
in ways that are literally impossible to predict. Cause and effect are no longer clearly linked. And this accumulation of complexity and tight coupling ultimately leads to a state of emergent gridlock. This is where the system effectively seizes up under its own weight. In a tightly coupled system, accidents become, as the sociologist Charles Perrow put it, normal. They aren't just possible, they're an inevitable property of the system's structure. It's no longer a matter of if a failure will happen, but when, as small, unforeseen interactions cascade into a major event. At this stage, the system can also be described as computationally irreducible. This is a state where there is no simplified model, no formula that can accurately predict the system's future behavior. There are no shortcuts. The direct consequence of this is that reliable prediction is simply no longer possible. You cannot know for sure what will happen if you make a significant change, because the web of dependencies has become far too complex to fully map out. And if the only way to know what a change will do is to actually make the change and see what happens, well, the risk of causing one of those normal accidents becomes immense. This creates gridlock. Any meaningful reform is seen as too dangerous, so the system becomes frozen in its overly complex state, essentially unable to be fixed. So, what does this entire process tell us? It suggests that maybe we should reframe our understanding of what this extreme complexity really signifies. Unmanageable complexity, therefore, is not necessarily a sign of failure or poor design. It is the accumulated result of numerous successful adaptations. Each layer of complexity represents a rational response to a past pressure. The very same processes that allow a system to survive and grow are what can eventually lead it to a state of gridlock. In this view, complexity isn't the problem. It's the shadow cast by adaptation itself.